Now, let me explain the calculation of the stability factors for the most popular circuit, self-bias. So, this is the self-bias circuit, and we have represented this entire circuit in this way using the Thevenin representation, because if you want to calculate the operating point Q, which is having the coordinates of VC and IC, you have to apply KVL for input loop as well as for output loop. So, to apply the KVL for this input loop, we have used this Thevenin theorem representation like this. What is Thevenin's theorem? Any circuit can be represented by a voltage source in series with a resistance. How much is the voltage here? The voltage across R2. What is the voltage across R2? VCC divided by R1 plus R2 is the current flowing through this multiplied by R2. So, V is equal to VCC divided by R1 plus R2 multiplied by R2. This is the voltage. And R1 and R2 are the parallel resistances. So, if you take this equivalent resistance of this R1 and R2, it becomes RB. So, RB is equal to R1 R2 divided by R1 plus R2. So, now it is very easy to apply the KVL for this loop, because if you want to calculate the input current here, and you have to apply KVL. So, by writing the KVL for this input loop, you can write here the applied voltage V is equal to IBRB plus VBE base to emitter voltage VBE plus the voltage across RE. What is the voltage across RE? RE multiplied by IB plus IC, because IE is nothing but the sum of base current as well as collector current. That's why you can say that this is IB plus IC into RE. So, this is the KVL for this input loop. Now, from this I want to write down the expression for the IB. So, how to write down the expression for the IB? V minus VBE is equal to IBRB plus IBRE plus ICRE. Now, V minus VBE is equal to IB into RB plus RE plus ICRE. I want to take to the left side. So, plus IC into RE. Therefore, what is the value of IB? IB is equal to V minus VBE minus ICRE divided by RB plus RE. This is the value of IB. This is the value of input current IB. If I want to calculate the stability factor S, already you know the generalized expression for the stability factor S is equal to, what is the value of S? S is equal to 1 plus beta divided by 1 minus beta into dou IB by dou IC. So, this is the expression for the stability factor, generalized expression for the stability factor. Here, in order to get the stability factor S, I have to differentiate IB with respect to IC. IB equation is readily available. So, that is why dou IB by dou IC is equal to, how much is the value? It is constant 0. It is also constant 0. The only thing is this term which comes into the picture. With respect to IC, it becomes 1. That is why minus RE by RB plus RE. Minus RE by RB plus RE. So, this is the factor we require to calculate your S. Therefore, what is the value of S? S is equal to 1 plus beta divided by 1 minus beta into dou IB by dou AC. What is dou IB by dou AC? That is minus RE by RB plus RE. Minus and minus becomes plus. Therefore, S is equal to 1 plus beta divided by, and it becomes plus 1 plus beta times RE divided by RB plus RE. Just substitute and simplify this. Therefore, S is equal to 1 plus beta, and you take it to the upper one, that is RB plus RE divided by 1 plus, means RB plus RE plus RE plus beta times RE. Therefore, your stability factor S is equal to 1 plus beta into, I would like to take you RB as a common, RE as a common. Therefore, RE into 1 plus RB by RE divided by, this is actually RB plus beta plus 1 times RE. I want to take RE as common here. Therefore, it becomes RB by RE, and it will be gone, and it becomes RE. RE and RE will be cancelled. Therefore, what is your stability factor? S is equal to, stability factor S is equal to 1 plus beta into 1 plus RB by RB divided by RE, total divided by, you can say this is 1 plus beta plus RB by RE. So, this is the expression for the stability factor for your self-bias circuit. Very simple, friends. Just write the KVL for the input loop. You are going to write your base current expression, and in the generalized expression just substitute what is dou IV by dou IC. Now, some approximations I am going to tell you. This is the stability factor S. This is the stability factor S for your self-bias circuit. Now, I would like to tell you, depending upon the approximations, how it changes. So, you can say, if this is RB by RE, if you are taking this RB by RE value, then if it is very, very less than 1, then you can see it can be neglected. So, if RB by RE is very, very less than 1, that means it can be neglected. So, RB by RE can be neglected here, and this also can be neglected here. 1 plus beta by 1 plus beta means it becomes 1. Therefore, S becomes 1. It is the excellent circuit because the stability factor is very, very less for this approximation. If RB by RE is extending to infinity, then what is the value of this? If RB by RE and RB by RE, if you take the common factor here, then that will be cancelled. Then if you are just substituting RB by RE tending to infinity, then S becomes 1 plus beta. S is equal to 1 plus beta. The stability factor is very, very high. That means more unstable. So, just by taking the values of the resistances, we can make the same circuit as a stable as well as unstable. Here, if you take the circuit here, it is more stable, S is equal to 1. But whereas here, S is equal to 1 plus beta. And another approximation, if 1 plus beta is, this 1 plus beta is very, very greater than this, that is RB by RE, this value, then it becomes S is equal to 1 plus RB by RE. That means it is independent of this RB by RE. So, just now I told about the 3 stability factors depending upon the approximations. If RB by RE is very, very less than 1, then it becomes S is equal to 1, more stable circuit. If RB by RE is tending to infinity, stability factor S is equal to 1 plus beta. If 1 plus beta is very, very greater than RB by RE, S is equal to 1 plus RB by RE. This way, the stability of the circuit also changes. By taking different values of the base resistance and emitter resistance, you can change the stability of the circuit also. So, this way you have to calculate the stability factor for our self-bias circuits. Okay, now we are going to just calculate S dash. What do you mean by S dash? S dash means change of collector currents with respect to VBE. Okay. Now we are calculating the stability factor S dash, which is defined as the variation of the collector current with respect to the base to emitter voltage, keeping IC naught and beta constants. So now write down the KVL once again for this input loop. V is equal to IBRB plus VBE plus RE into IB plus IC. This is the KVL for this input loop. Here I want to write this IC for the common emitter configuration. IC is equal to beta times IB plus beta plus 1 times IC naught, that is the reverse saturation current. Just substitute this equation in the first equation. Therefore, V is equal to IBRB plus VBE plus RE into IB plus IC means beta times IB plus beta plus 1 times IC naught. This is the reverse saturation current. Reverse saturation current into RE. Into RE. Now take the IB as a common, then you can write down this expression. V is equal to IB into RB plus. So here IB into RE. IB into RE. So you can say RE plus beta times RE. Beta times RE plus VBE plus this is beta plus 1 times RE into IC naught. Beta plus 1 times RE into IC naught. So this is the expression for this IB. So V is equal to IB into RB plus RE plus beta times RE plus VBE plus beta plus 1 into RE into IC naught. Okay. Now I have to do the differentiation with respect to VBE. So I want the IC expression, but here you are having only IB. So in the place of IB, I can write down IC is equal to beta times IB. Therefore, V is equal to, this can be written as IC by beta into RB plus, I can take RE as a common, beta plus 1 into RE plus VBE plus, this is beta plus 1 into RE into IC naught. IC naught. Beta times V is equal to IC into RB plus beta plus 1 times RE, beta plus 1 times RE plus beta times VBE, beta times VBE, okay, plus beta times beta into beta plus 1, beta plus 1 into RE into IC naught, RE into IC naught. Now I want this differentiation of IC with respect to VBE. So this is constant, it is 0, derivative with respect to IC is 0. So this is equal to RB plus beta plus 1 times RE, this is the differentiation with respect to IC is 1, plus it is also 0. So but here beta into dou VBE by dou IC, dou VBE by dou IC, and the differentiation of all these constants is 0. IC naught is constant and beta is constant whenever you are evaluating with respect to VBE. So this is the expression that is remaining here. Therefore, dou VBE by dou VBE divided by dou IC is equal to minus of RB plus beta plus 1 into RE divided by beta. Therefore, I want the stability factor S dash. S dash means it is in the reverse direction. It is equal to 1 by S. Right? 1 by S dash. I want S dash means if the reversal of it, the reciprocal of it, S dash is equal to minus beta divided by RB plus beta plus 1 into RE. Now I would like to divide numerator and denominator by RE. So that is equal to minus beta by RE divided by RB by RE plus beta plus 1. Therefore, the stability factor S dash is equal to minus beta by RE divided by RB by RE plus 1 plus beta. This is. Now you can say, if 1 plus beta is very, very greater than this, I am taking the assumption once again, friends. This is the expression for your S dash. This is the finalized expression for the S dash. Now I would like to tell you, if 1 plus beta is very, very greater than RB by RE can be neglected. Then 1 plus beta will be remaining. So compared to 1, beta is very, very high. So it becomes beta. So totally the denominator becomes beta, and that beta and beta will be cancelled. So when 1 plus beta is very, very greater than RB by RE and beta is very, very greater than 1, if you take these two assumptions, 1 plus beta almost equal to beta, beta and beta will be cancelled, then it will be equal to minus 1 by RE. So this is approximately equal to minus 1 by RE. Therefore, S dash is equal to, finally, S dash is equal to minus 1 by RE. This is the expression you have to use for the stability factor S dash. S dash means you know very well, it is the variation of IC with respect to VBE. This way you have to develop the expression for your S dash. Similarly, you take the same expression here, this is the same expression you try to take here, and if you are going for the next stability factor, that is nothing but S double dash. So what is S double dash? S double dash is equal to dou IC by dou beta when IC naught and beta constants. These two things are the constants. S double dash is equal to IC into S divided by beta into 1 plus beta. What is its value of S? S is nothing but the stability factor S. That S is nothing but the variation of IC with respect to IC naught. Here S is equal to dou IC divided by dou IC naught. Already we got this. So this is the way of calculating the third stability factor. So in this class, we have calculated the stability factors for the self-bias. 3 stability factors, S, S dash and S double dash. So this is the basic equation you have to use for calculating all these stability factors. Your IC is a function of 3 parameters. One is IC naught, another one is VBE, and the third one is beta. Dependency on IC naught is nothing but S, stability factor S. Dependence on VBE is nothing but your S dash, and on beta it is S double dash. Now I would like to write the expression, the change in the collector current due to the changes in all these parameters. So I can say that delta IC, change in the collector current, is equal to dou IC by dou IC naught, that is dou IC naught into delta IC naught plus dou IC by dou VBE into multiplied by, this is delta VBE plus dou IC by dou beta, the third parameter, into delta beta. So what do you mean by dou IC naught? It is yes. That's why delta IC change in the collector current is equal to S times, because it's the definition of S times delta IC naught plus S dash times delta VBE plus S double dash times delta into beta. So this is the expression which is giving the variation due to all the parameters. It is also the most important equation to calculate different parameters in your feature. Okay, I hope you understood the way of calculating the stability factors for any type of biasing circuits. Okay, thank you.